My name is John Trippier. I manage all things BD and partnerships at Databricks. I'll be the moderator of this session on data science. We have three very good talks. The first one is going to talk about large volumes of data and how you handle that into the context of the automotive. The second one is going to be more about finding outliers. And the third one from Verizon is going to talk about indexing into data science issues. Two very good topics. The first one, Till and Miha are going to talk about something specific. If you ever wonder or if you ever thought about building a self-driving car, the complexity of that and how much data comes into that and what kind of new algorithms you need for that, they're going to tell you about that. We'll do Q&A at the end of the session. Thank you. Please welcome Till and Miha.
Okay, thanks for the introduction. Thanks for having us. I'm Till, and this is Miha, my colleague. We're both from a company called Norcom, based in Munich, Germany. And we're going to talk today about the projects we did with the automotive industry in the last 2 to 3 years. So just a big, quick background of us. So Norcom is a company. We have around 130 employees. The company is quite old already for an IT company, I would say. And we have a background in information management, so we had a lot of projects with the media industry in the last 10 years. We have a big branch that is doing big infrastructure consulting for big institutions in Germany mostly. And and now we are, since these 2 years, let's say, we are building up this branch on big data with a focus on the automotive industry. And this is what we are going to talk about today. So where's the data coming from in the automotive industry? It might not be immediately obvious, even though the last talk in the keynote speech already kind of gave a hint. So there are basically three kind of major data sources in the automotive industry where that's really revolving about the car, if you don't talk about the financial part of it. And this is coming firstly from the car development, and especially now with autonomous driving, you really get a lot of data because, well, sensors are cheap and they have really thousands of sensors in their cars, and with the cameras and radar systems, you really add up in the data rates. So currently, if you really have to store the raw data for algorithm development, you get data rates up to 2 gigabytes per second. So if you have an 8-hour drive to test your car, this is adding up to 60 terabytes per day, basically. And so we're dealing with the 3 major car manufacturers in South Germany, and one of them made an estimation for building an autonomously driving car, and they are expecting about 55 exabytes of data to process until you get a viable product, basically. So this is one kind of source. Here we talk about relatively few cars so real prototypes. Then once the car is developed, so that's currently what's happening now with the highly assisted driving cars, they build a small fleet of these cars and test them, so drive around very, very quickly, very large distances. Generally, before the car really goes into production and is sold, they usually drive around for 10,000 hours of driving hours to really test all the corner cases and all the special events so that the assistance system, for example, don't overlook any kind of cars or something like that, so it's really a safe product. And here the data rate's a little bit lower because you don't really have to store raw images from the sensors, but kind of compressed data. But still, there are significant, like 300 megabytes per second. And so after all these kind of test drives for one car model, you arrive at around 10 petabytes of data that have to be processed and verified. So this is running. Yeah, you have a lot of test cars which are running all over the world. And finally, once the cars are sold, they're out in the field and they're sending back data via mobile devices. The actual data sets are getting smaller, obviously, because the data connection is rather thin, let's say. But here you have thousands. Oh, sorry. You have hundreds of thousands of cars that send back data, and this is kind of the whole IoT business that's kind of starting there. Right. So yeah, and these are the this is kind of our management always calls it kind of the data tsunami coming from the automotive industry. That's why this picture is there. Okay. So how the data is really looking like? That's coming from the car. So in a car you have several data sources again, like you have a camera system, you have kind of a control unit that controls the engine, you have a control unit that controls the wipers, you have a control unit that controls the gearbox. So any kind of, you have a various ECUs, electronic control units in the car, you have a multimedia system, maybe some, all kinds of services. And all these systems communicate through via a bus system in the car, or several bus systems. So they send post messages on this bus system, and other people are receiving these messages, other units. And if you want to get the data out, you kind of plug a box onto this bus system and start listening. And what you get is kind of the stream of messages, very familiar to everybody, I guess. And now we have two, in this talk, we're going to talk about two types of analysis that are done currently already in the automotive industry, and that now we kind of try to bring into the big data world and kind of make them possible also in the future when data rates are growing. So one is kind of, you really do kind of, say, classical multivariate time series analysis. That's what I'm going to talk about first. And then second, Miha is going to talk about how we use that to fuel a state machine and run that and then analyze state machines in parallel. Okay. So yeah, that's, this is basically my part of the talk. So we did projects with several car manufacturers in the last years. And these were usually kind of discovery projects where we kind of test whether Spark is actually a viable tool in this domain. And during these projects with different car manufacturers, we realized they all have the same problems, which is pretty clear because they all build cars, basically, and do it more or less in the same way. And kind of during this project, we built up our own library of tools that work with Spark to be faster in the next project, basically. And this kind of developed into a project and a product on its own, which we call Sense now, and which we hope also that the car engineers themselves will be able to use at some point. So it has to be kind of a rather simple API, and we try kind of to hide all the complexity that's coming with Spark, so that they can focus on their problems. And this is what I'm going to present to you now. So yeah, this I already showed. So what's happening? So one type of using this data is kind of to sort it into the different measurement channels that's happening. So in the car, for example, the engine control units also send messages around how fast the engine is spinning, the rotations per minute. We have set messages around the speed, some various physical properties. Sorry. And also like status flags, like the air condition is on or off. So this is basically how the data is looking like. You have time series, which are not on a common time base. They have different sampling rates. The sampling rate might even not be equal. Sometimes it's basically depending on how fast the engine is rotating, for example. And it can be, and usually we find kind of in a measurement file that we get from the automotive industry, we get around 700 to 5,000 signal types, so channels like this. These time series might have millions of entries because you have a long, say, one 8-hour drive, so 1-day drive, and you have sometimes 10 to 100 hertz measurements. And then you have hundreds of these measurement drives for one test car, for example. So what are the typical questions that the engineers have to their data? They range from very simple ones. They want to know in a certain test drive, did a certain signal pass a threshold or not? Kind of did the oil temperature go above 100 degrees, or the temperature in the diesel particle filter, what was it? Was it above 700 degrees or something like that? Or did a certain signal run in an interval or not? You also might, so in this category, we also put pattern search, so maybe they look for specific driving situations. They want to have all situations where the car stopped at a red light and then started going again. And so they can further analyze these kind of situations. Then we have aggregation reporting, very classical, like you have a test car that has driven now 150,000 kilometers. What's the distribution of the speed and the temperatures in the car? So basically to check what kind of parameter space, how did we fill the parameter space for our testings. Then we're getting to more interesting things like classification. We had, for example, one project that was around gear shifting quality in a car with automatic gears, automatic gearbox. And sometimes, if it goes bad, the car is kind of buckling when you shift, especially in the lower gears. And they wanted to kind of find these events and then understand what's happening, because that's obviously a very bad user experience when this is happening. So we kind of found all the gear shifting events that for an 8-hour drive that might be a couple of hundred or thousands, and then try to classify them in good ones and bad ones. And then finally, once you have that and you can convince also the engineers that this makes sense, what we found, then we can look for correlations. For example, why did it go bad? We do root cause analysis. This is basically what we do here is mainly kind of you really have to sit down with the engineers and kind of bring together domain knowledge from them with kind of our analytics knowledge. Right. So I said we kind of build up our own kind of Python or our own library that kind of exposes an API to quickly solve these kind of problems. And this API we built, it's Python-based, so we use PySpark mostly. We try to reduce the complexity by kind of focusing on this specific kind of data and also this specific kind of questions that are asked. We want to use lazy evaluation, obviously, because we want the underlying engine is Spark. And I'm going to talk now quickly about the kind of most important concepts that we use. Expressions is clear for lazy evaluation. And then we have this thing called data extractors. So, so this is how basically how we work, or how our API is looking like. So just a quick code snippet. You have some context, which we take kind of the default values here. For example, the Spark context is included in there. You put that into, and then you load your data here. For example, it's stored as a Parquet file. So this is not one test drive, sorry, that's a typo, but it's kind of a large number of test drives, say for one car. And we load that, and then we create these things called channel extractors. These are the data extractors that I will talk about in a minute. And then we build up our expression, which is here. We are interested in the speed channel, but only in those times where the oil temperature is larger than 90 degrees. And then we want to have a histogram about that, so the distribution basically. So here, this is so this expression is basically here shown as a expression tree. So we have kind of data extractors on the leaves and kind of a float expression. And then we have mathematical expressions and functions that we can kind of build in together. And yeah, and then we kind of throw this expression onto our old data set, which contains basically a data frame, which is created here and is evaluated and gives back the result. And yeah, and so yeah, keep in mind the idea is to kind of make a very simple, straight-to-the-point API for engineers as well, so that they can also write their own scripts basically. So what's the point about the data extractors? So the data is stored in some specific format in our Parquet files, optimized for these kind of requests. And so to hook and these data extractors, so the channel extractor is one example for that. Is basically the hook index expressions to kind of connect to the data. And the specific thing is also that when we talk about a speed channel and the oil channel, we obviously mean the same. So they are kind of in this data, we have a lot of speed and a lot of oil channels from different measurements. And we obviously have to bring together those, again, that belong to the same measurement. So this is all kind of handled by the data extractors, which I can then kind of feed in code to Spark and run a Spark jobs. And so that's kind of the main task for these data extractors, but there are a couple of subtle things or more problematic things that they have to handle as well. For example, one engineer encodes when he takes the data, he encodes the speed channel as speed. The other one calls it vehicle velocity something. And somehow we have to know that these are referring to the same physical measurement in order to kind of analyze the whole database. Second, there are unit problems, like you can have the speed in miles per hour or kilometers per hour or meters per second. So you have to handle these kind of conversions. And finally, you have physical channels like speed or rotations per minute, where you can have, for example, linear interpolation between the data points, and you have to interpolate a lot if you have these non-common time bases. Sometimes you have status flags where you don't want to have linear interpolation, where it's more like in the talk yesterday where we heard that kind of we take the last data point in the other time series. We would call that zero-order interpolation. Okay, so So these are basically our main concepts that we kind of use to kind of abstract the way Spark basically for the engineers. We have then a kind of a certain idea of or how we do our projects. And this is a kind of a workflow that we follow in our projects. So we usually have an ingest. So we don't take the data ourselves. I should say that, I guess, again. We're not in the cars, but we get the data from the engineers in their favorite format, which is usually some obscure automotive format. MDF is a very famous or widespread one, or ATFX. So these are automotive-specific formats, often proprietary. So we have to convert this data into some kind of format that is readable by Spark or generally kind of big data tools. And this is, I would say, this part is, as always, kind of one of the major workload. And then kind of the analysis start. We filter out the data sections that we are interested in my example with the gear shift. It's the gear shift events that we want to extract, and maybe also kind of we're only interested in cars that have a certain software installed or a certain version of the software installed. That's usually one of the criteria that are relevant. And then we do some feature extraction. So, for example, in this case, it was kind of a Fourier transform. We want to see whether we have some oscillations in the rotations per minute, which hint at kind of buckling of the car. And once we have this data, we can kind of go back to finally, we can go back to the kind of classical tools that are out there. Basically, for example, the MLlib for Spark or your favorite data science toolkit. So here, obviously, we don't reinvent the wheel. That wouldn't make no sense. So, but these steps are generally doable within our kind of time series API. Okay, so this is basically what I wanted to tell you about how we kind of our first section of problems or what we deal with that we deal with in the automotive industry, where kind of a big issue is kind of getting the engineers into the game as well, and not kind of scaring them away with all the IT problems that come up. And now Miha is going to talk about a more in-depth problem.
Oh, thanks, Dale. Hi, Miha. Not sure it's much more in-depth problem necessarily, but it's a bit something more specific since we're here in a data science meetup group. Wanted to kind of share a little bit on the algorithmic side of what we do, which is related to what Till was presenting, but it's not exactly that thing. So I want to talk about state machines in the automotive industry. It's something I haven't seen so much around in Spark, so I thought that might be something interesting. State machines, for the ones who don't know it, it's sort of it's a mathematical model of how to describe things, and it's used quite a lot in automotive and engineering in general. Essentially, it tries to represent a certain system, in our case mostly the car, by its states and the transitions between those states. The simple one you can think of, car being turned on or being turned off, that's a state. Transition, you know, the switch that you do. That's a very simple one, simplistic one. There's many others. Till was mentioning electronic control units before. Each of them essentially implements its own state machine, and then those state machines are talking to each other and needs to be coordinated somehow on the computation bus. And at some point, you need to analyze this. Yeah? You have those communication protocols that you need to make sure they adhere to each other. And that's one of the major problems that we have, or rather that we were working on as well. So the goal there, it's to analyze, given the logs that you've seen, you've seen the logs of those messages here, were they okay? Were the messages coming at the right times? Were they giving the right information and so on? Now, the state of the art, or rather with the current status quo approach is to replay the whole drive. So you have your log of the messages, and now you have some sort of software solutions that kind of let you replay everything that was going on. And they give you some sort of hooks that they say, okay, there was a transition in the state. So that kind of allows you then to go message by message and making sure I'm in this state, was that message correct, and so on. And then you find a message that kind of gives you the idea that you should transition the state, you transition your state, and so on and so on and so on. So you can test it in this way, and it's inherently sequential thing. And a question then, now, when the density of messages is increasing, and you have more ECUs, so more control units. The control units are sampling with a higher resolution. The messages are bigger. It's harder and harder to do this replay and much faster than real time. So if you have 8 hours of car drive, you need 8 hours of analysis time, and that's becoming too much. So ideally, you want to parallelize that. Yeah, you want to be able to kind of cut that in pieces, like we show here, and run those analysis on the separate pieces. The obvious parallel solution. Problem there is that the state machines aren't that obviously parallel, because the question is always, what's the state when you start? And as soon as you kind of break it down, in the beginning you had this problem as well, but you kind of soon can solve that, and from then on you always know in which state you are. Here, if you're always starting with an unknown state, and then going further, that's difficult. So for what we try to do, and it's something I'm going to show you here, is given this thing with certain state transitions, can we first find when those state transitions occurred? So it's going to be kind of a generalized way of how we do this state transition finding. Now, states and the transitions, they can be encoded in different ways. So here I show 3 ways of how they can be encoded in these log messages. The simple one would be, and it's not shown here, is you have a message that says, okay, now we transition the state. But that's not normally how things are. What you normally have, one way, is you have somewhere the state explicitly encoded in a message. So each message will have a timestamp and the state, some other information as well, but this is important for us now. So this one says we're in a state 0, we're in a state 0, oh, we're in a state 1. So the transition has happened here. We say it happened at 0.03 because that's the first time we measured the state, that transition. And that's okay, right? That's how you can do it. Here we always transition between 0 and 1, just for simplicity levels. Now, another way of how you can encode that, or how it is encoded, is via a value on the message. So the message here, values, is not a state anymore, but it's a floating number, if you will. And you have your thresholds defined, and you say, whenever I cross that threshold, I change the state. So whenever I'm below a certain threshold, I'm in that state. Whenever I'm above this threshold, I'm in the other state. Now, there is sometimes this grace period in between, this hysteresis, that kind of prevents from having your states randomly changing on the noisy data. And that kind of makes things a bit harder as well, because now this state is in kind of, this message, sorry, was in, if you look at it in its isolation, you don't know which state it's on. You have to look back and see which state you were before in order to know where you are in that state. And then another way of how the states are encoded, they're encoded implicitly via the times of the messages. So essentially, state on would be when messages are coming, state off where messages are not coming. So in order to know when your state off was occurring, you need to look at the pauses, the silences in between the messages. So now quickly to a method that a very basic method that we are working with, and it's turned out to work quite well for us. I'm going to quickly show how we do that with Spark. So we take that original encoding with zeros and ones on states, and here we see now the problem, right? So we want to find those timestamps, those messages, because this is where the transitions happened. But when we parallelize things and we first cut the messages into partitions, you have an issue here in the beginning. You don't know what your previous state was, so you don't know if was this a transition or not. Here it wasn't, because the previous was 1, but it's in a different partition, so you don't have access to it. Here, for example, you have a different experience where you did actually have a transition, but again, you wouldn't know it is because you wouldn't know what a previous state is. So how to solve that in this one is, one way to do that is when you do your map partitions, you don't just map out the transitions that you find within your partition, but you also map out the first and the last message of each partition. And what you get out then is a list of transitions and the list of potential transitions, so to speak. So what we do typically is we just collect those on driver. So we go out of the parallel phase and just simply then do a final cleanup where we now can have them sorted and look through them and just take out everything that's not actually a transition. So this approach has its benefits and its flaws. The main flaw being that we at some point collect everything on a driver. So if you have a lot of transitions, you can get your memory overflown. You need to clean up the serial, so if you had a lot of cleanup to do, that would take you would lose your parallelization there, parallelization power. But turns out for our problems, that's what mostly works. There's a couple of alternative solutions that we've played around with. We tried them out, but they were in fact mostly less performant, or we just couldn't use them. One is with using some of the windowing function that lets you kind of look at the previous messages and the next messages. Problem here is that you don't always know how far in the past you have to look at, so your window size is unknown. Another thing you could do is you could broadcast those borders out and then do another group by, and that kind of get expensive first and doesn't generalize well either. And then there's the one that would probably generalize the best. I can't go into details now, but if you're interested, this one I kind of like the most, but unfortunately it makes things quite complex soon, and we kind of figured it doesn't make sense. The complexity is too high in the end. Anyway, so our experience with this analysis of state machines is you try to keep it simple. That simple algorithm worked quite well. Performance was quite important for our client in this case, so we first actually did that with Hive. And especially because we don't need to just look at the transitions, but we also then need to use and reuse those messages to check if they were in the right positions. We have to iterate several times across the data. So Spark is obviously a better solution there because you have everything in a memory typically, and that caching helps you a lot. So PySpark, because we're Python guys primarily, but again, given that we're working with RDDs and that performance was really crucial, we're now moving to Scala as well. Using RDDs, you see that you still have about a 5 times speed up going to Scala from Python. So that's kind of what we've learned from it. I have a sample code for the specific algorithm I was presenting available, both in Python and Scala here at GitHub if you want to look at it. The actual state machines and so on, they're a bit more complicated. So this was really a generalization of it, but it's a nice toy model to start working with in a topic, I thought. So yeah, in summary, we work with automotive data, and it turns out it is big. It's getting bigger and bigger, especially with this autonomous onset. And the data problems there are sometimes a bit specific. So some of them are the ones you would know from the conferences, but some of them are becoming more specific, like the state machines, for example. But they're quite fun, and they can be done in parallel, but they require a bit more more work, let's say. And yeah, we've now kind of prototyped, kind of made our clients realize it works, and now it's going into the production. So yeah, thanks for your invitation for the organizers. Thanks for coming, and yeah, that's it.
I think we have time for 1 or 2 questions. Any question? All right, just wait for me.
I think we know when.
Hi.
Hi.
Thank you. Really interesting talk. When you were discussing state machines, you talked a lot about the problem of aligning state information with time series information in different memory partitions. And essentially that's a problem of labeling, right? You want memory partitions to be consistently labeled with states, so you can pass them to a machine learning algorithm. I wondered if you'd done any work trying to infer labels in an unsupervised way from time series data alone.
So I haven't completely heard the question well, but we definitely haven't done much machine learning on the states part. So for the state machine stuff, we've mostly been implementing the tests that validate the protocols, communication protocols. So there wasn't much machine learning done, no, especially not in unsupervised fashion. Typically, when you go to these R&Ds and protocols, it's anything unsupervised. The word unsupervised sounds very scary to the automotive industry, as you can imagine. I'm not saying that there isn't a potential there, but no, we haven't done anything there. Yeah.
All right, last question. All right, I'll just ask one. If I'm a data scientist and I'm getting into a new project, I'm sensor-based and time series, what is the one mistake you expect me to do?
So the data, if you work with time series, you kind of new to time series, and the one mistake.
Well,
Your mistake is to expect it comes as CSV, I think. But it's usually kind of so you get your time series in some kind of weird binary format. I think kind of generally, or at least kind of in our domain, that the analysis themselves were rather simple, but but getting the data into the format is, I think, kind of the major problem.
Well, thanks very much. Please, I'm sorry, Miha. Please welcome me in thanking Miha and TL for the presentation. Thank you.